What if a material inside a satellite could do more than just occupy space? What if it could be lightweight, protective, and also help us detect when something is changing inside the structure? In aerospace, every gram matters. Materials must be light, stable, and reliable under demanding conditions such as vacuum, temperature variation, or radiation. But many conventional foams are passive. They can absorb energy, but they do not actively tell us what is happening to the structure.
My project, Developing a Functional Foams for Aerospace Environments, explores a different idea, creating a lightweight foam that combines structural function with an electrical response. The goal is not only to develop a foam, but to study whether the foam can become a smart material. The material is based on chitin foam, a bio-based polymeric matrix, combined with a functional filler such as carbon sepolite known as CARSEP, and a multi-wall carbon nanotubes. The idea is that these fillers may form a conductive pathway inside the porous structure. When the foam is compressed or deformed, those pathways can change, and that change may be detected electrically. To produce the samples, the components are dispersed in water. Chitosan is dissolved in acid medium glycerol and is added to improve flexibility. And the suspension is molded and freeze-dried. The process creates a porous lightweight structure. Three formulations are being compared: pure chitosan, chitosan with CARSEP, and chitosan with CARSEP plus carbon nanotubes. At the characterization stage of the project, the foams are measured for geometry, mass, apparent density, and electrical behavior under controlled compression. During testing, the samples are compressed progressively to 50% of the formation, while electrical response is recorded. This allows to evaluate whether the materials show piezoresistive behavior. In other words, whether the formation produces a measurable electrical signal. To bring the test closer to our space conditions, the samples are also exposed to thermal cycle, 2 hours in cold conditions at minus 20 degrees Celsius, followed by 2 hours in hot conditions at plus 60 degrees Celsius. So for this, one possible application is an internal functional layer inside a CubeSat operating in a low Earth orbit. In that context, the foam would not replace the main structure. Instead, it could act as lightweight internal coating or component that contributes to protection and potentially damage or deformation sensing. So the purpose of the project is clear: to explore how sustainable lightweight materials can be upgraded into multifunctional systems, because the next generation of aerospace materials should not only survive in space, they should help us understand it. Thank you.